Welcome to Pod 4 Journal Club. Today, we're diving into a really fascinating paper that looks at how these powerful AI coding tools are completely changing the way we build software. We're going to explore how they're making huge design decisions for us, often without us even realizing it, and basically creating entire software architectures, all on their own. Let's jump right in. So, this whole thing really kicks off with an idea you might have heard of called vibe coding. The concept is simple, but kind of wild. Instead of meticulously writing every single line of code, developers just describe the vibe of what they want in plain English. And then the AI agent does all the heavy lifting, turning that feeling into working code. It's a massive shift in how we think about programming. But here's where it gets really interesting. This paper argues we've moved way past just vibe coding. We are now in the age of vibe architecting, and this is a whole different ballgame. We're talking about a situation where one simple sentence doesn't just create a function, it silently makes massive, totally unreviewed decisions that determine the entire blueprint for your system. Okay, so here's our plan for breaking this all down. First, we'll look at the hidden blueprints these AI agents are creating. Then, we'll walk through the paper's really clever experiment. After that, we'll unpack what they found, cover what we know and what we don't, and finally, talk about what this means for the future of building software. So, this leads us directly to the central, most important question the paper is trying to answer. What is actually happening when these AI agents become our system architects by default, without us ever explicitly telling them to? Well, think about this for a second. These agents are out there picking our core technologies. The frameworks, the databases, how we handle security. These are huge architectural decisions that human teams would normally spend weeks debating in meetings. The AI does it in seconds. And the craziest part, there's no paper trail, no design document, no explanation. You end up with a complex architecture created without an architect. So you might be wondering, okay, that's a pretty big claim. How did the researchers actually test this idea? Well, they came up with a simple but really powerful experiment to see how this vibe architecting works in the wild. I love this part because the setup is just so elegant. They gave an AI tool one single job: build a basic chatbot for customer service. The only thing they changed between tests was the wording of the prompt they used to ask for it. This way, they could isolate the prompt itself and see just how much of a difference a few words could make. All right, first up was prompt A. Super basic, right? Answer product questions from an FAQ. It's a very high-level goal. It just tells the chatbot what to do, but not really how to do it. Pretty straightforward. Now, for prompt B, they got a little more specific. They added a new rule. They didn't just want an answer, they wanted it in a very specific format called structured JSON with validation. Think of it like telling the AI it has to fill out a form perfectly every single time. It's a common way to make systems more predictable. And then there was prompt C, which took things a step further. This time, they defined the agent's capabilities. They basically said, hey, you have these special powers now. You can search a knowledge base, look up a customer's account, or pass the conversation to a real human. They were defining an interface for the agent. So, they ran the experiment with those three slightly different prompts. What happened? Well, the results were kind of shocking, actually. Those small changes led to wildly different systems, which perfectly demonstrates the paper's main point. Just take a look at these numbers. It's wild. The simple bot from prompt A was just 141 lines of code in 2 files. But by the time we get to variant C, the one with tools, we're looking at 827 lines of code in 6 different files. That is a nearly 6-fold explosion in the amount of code. And remember, all they did was change one sentence. And this shows us what all that extra code was for. Variant A was just the bare minimum, but the moment they asked for that structured data in variant B, bam, the AI decided it needed to add a schema validator and error handling logic. Then for variant C, it went even bigger. It added a tool registry, a decision-making loop, and even its own little database to keep track of things. Entire architectural components just appeared, dictated by the prompt. And this brings us to the absolute core of the paper's argument. The prompt is no longer just a request, it is the architectural specification. To make sense of this, the authors identified what they call 6 prompt architecture coupling patterns. Basically, 6 common ways your words get translated directly into system infrastructure. First up are the constraint patterns. This is what happens when you put rules on the AI's output. You ask for that structured JSON? Well, now your system needs a parser, a validator, and retry logic.
The authors call these contingent patterns because it's possible that as the AIs get smarter, they might not need all this extra scaffolding.
Next, we have capability patterns. This is when you tell the AI what it can do. The moment you give it tools, like in our prompt C, you suddenly need a tool router, another validator, and that whole agent loop thing. The paper calls these patterns fundamental because logically, you're always going to need this stuff no matter how smart the AI gets.
And finally, there are the context patterns. This is all about the information you give the AI to work with. Let's say you want to use a technique like RAG to ground the AI in your company's documents. Well, congratulations. You've just implicitly signed up for a pretty complex data pipeline to manage all that information.
Now, of course, no single study can answer everything, and good research is always upfront about its limitations. So let's talk about the fine print here to really understand the scope of what we're looking at. The authors are really clear that this was an illustrative study, not some massive, exhaustive experiment. It's a deep dive into one specific example using one AI tool and one model. And they're the first to say that this field is moving at lightning speed, so these findings are really just a snapshot in time. So with all that in mind, what are we supposed to do? This all sounds a little scary, right? Well, the paper doesn't just drop this problem in our laps and walk away. It actually lays out a pretty clear path forward. This right here is the heart of the problem, what the paper calls the speed review gap. An AI agent can build out a complex system in a matter of minutes. It would take a human team, hours, maybe even days, just to review and understand what it built. It's creating complexity way faster than we can keep up. So what's the game plan? The paper gives us some really concrete recommendations. First, we have to start treating our prompts like they are official design documents, because they are. They need to be code reviewed. We also need to get the agents to log their own decisions. Maybe we need some automatic guardrails, like if an agent is about to generate 1,000 lines of code, a human has to approve it. But the biggest idea is we need new tools that let us see the architectural impact of a prompt before any code gets written. And looking further down the road, the paper points to where the research community needs to focus next. We need better ways to even measure architectural complexity, we need smarter governance tools, and maybe the ultimate goal, figuring out how to get the AI to automatically generate the documentation we need to understand what on earth it just did. And that all leaves us with this one big, really thought-provoking question that just kind of hangs in the air. As these tools get more and more powerful, we have to ask ourselves, when your AI agent is your co-pilot, who is actually the architect?